In our last video, we saw how we could use arrays in unsafe ways in C programs, and we'll continue looking at some of these problem spots in C. So once again, I should probably mention here, make it clear that C was designed in this way. C was designed to be super flexible so that you can index beyond the bounds of an array. It was all it was sort of part of the plan that you should be able to use arrays in any way the programmer sees fit. The problem is that programmers will use it unsafely and not notice that they have used it unsafely. That's the problem. So the language, sure, it gives you total flexibility. That in itself is not a problem. It's just how you use it that becomes a problem often. So we saw that there were quite a few problems with this particular program, and I showed you, I purposely ran it on a Mac OS X machine to show you that there was a problem. And chances are you probably looked at this and saw that there are problems in these three spots. That's the way the array is used in these loops. That was where the problem was. And this is despite the fact that on a Linux system, this program will probably run and produce what looks like the right output. So let's take a look at that. I didn't show it to you running on a Linux system. So let's compile this program, GCC, I call it like 16-4, I believe. I hope that's the right one. See, compiles. Let me cat it to make sure. Like 16-4.c. Yes, that is the one. And if you were to run this / like 16-4, it actually does give you the right output. Okay, so it is exactly the same program that we ran before on a Mac OS X. Now I'm switching to a Mac OS X window, like 16-4, and it produces the wrong output. So in this particular case, although the program looks right, let me pull it up, 16-4.c. Although the program produces, although it looks like, well, you might be able to do all of this, no, we know from looking at this that, yeah, we started the wrong index, we checked the wrong endpoint at two different loops, and so on. So there are problems with this. Despite that, it actually does seem to give you the right output on Linux machines, but as we saw, if you run this, if you were to take this on to a Mac OS X machine, compile it and run it, yeah, you see the wrong output. Okay. So oops, went too far. Let's take a quick look at one other problem with unsafe array subscripting. Now this is a little bit harder to see, and also it has different behavior whether you're on a Linux machine, and if you're on a Linux 64-bit versus a 32-bit machine, you will see different results. So there is some hardware dependence, just like in the previous program there was hardware dependence between the Mac OS X machine and the Linux machine. So these are the kinds of problems that you run into in practical C programs. You'll get very dramatically different behaviors if you're on different hardware. That is, even if you use the same compiler. Okay, so let me cat out this next program, like 16-5.c, and in it what I have done is I have set up an array and a variable. Declared two things, an array of size 10 and a variable, and then I've set up loops that will manipulate this. And you can take a look at this. All it supposedly does is sets the elements of an array to 0, and then prints out those values, supposedly. And it was C. Let's see what happens. GCC, in this case I called it like 16-5, 16-5.c. It compiles, no problems. And then I'm going to run it like 16-5. And guess what? It just sits there. And you can open up another window and run a program like top. And let's just do that. If I can. Might not happen super fast. One reason is that, and you can probably tell from the output, it is stuck in an infinite loop, and an infinite loop takes up all of the CPU power. It doesn't do anything, just sits and works away, grinds away in a loop. And so in this case, it's keeping the CPU busy enough that the system is not actually even responding to me. If you run into a situation like this, what you want to do is Control-C it. So I'm going to hit Control-C, and it stops. Okay. So let me take the exact same program and run it on a Mac. And what you will see is there's slightly different behavior. So cat like 16-5.c. Okay, it is the exact same program. Let me compile it. -o 16-5 like 16-5.c and run it like 16-5. And actually it has completely different behavior. It doesn't go into an infinite loop, it just sort of exits. It doesn't print out anything. Okay, so let's take a closer look at this. Sorry about that. Find my notes. There it is. Okay, so it turns out this is the part of the code that you have to focus on. Remember that I said arrays are stored in the stack. So what you have here is, if n is 10, you have 10 ints stored in the stack. And then remember, if you have an int I, that's also stored in the stack. So what this means is that there's 10 ints followed by another int for I, all stored in the stack in sequential order, it turns out. So that when you go into a loop and let's say you go past the bounds of the array and into the next spot after the array, which is what you will end up doing if you have I less than or equal to n, where n is the size of the array. Remember, once again, if you have an array of size 10, you have to go from 0 to 9. You should not go to index 10. If you do, if you have a erroneous bounds check like this, then what you will end up doing is you will write 0 to a sub 10. There is no a sub 10. So it turns out what you're doing is you're writing a 0 into this into this location for I. You're going outside the bounds of the array into the next location and setting I to 0. So what does this do? What this does is you go through all the loop indices, the values that the loop should take. You go past the bounds and then you set I back to 0. So what happens is you bump up I, and then I is back to 0. It might go up from 0 to 1, and then you check its 1 is less than 10, and you keep going, and then you hit a sub I. I goes to 10 again, goes beyond the bounds of the array. You reset I to 0, and so on. So what you're doing is you're stuck in an infinite loop because you are writing to memory outside the bounds of an array, and that memory just happens to be the loop index. Very subtle bug. These kinds of things are just about impossible to debug unless, of course, someone points it out like this, or if you happen to look at it and you spot it. These things are kind of hard to spot. That's why I'm telling you here. Okay, so this is another example of unsafe array subscripting. C allows you to do this, and who knows, maybe some programmer wants to use indices and arrays in this way. Certainly makes it hard to figure out what a program does, and so probably don't want to do this. It just so happens C lets you do it. Okay, like in other programming languages, C does allow arrays as arguments to functions. So, for example, you can set up a function f with an array A, and almost always you have to pass in the size of the array, and you want to get that right when you call the function too. So this is because, unlike Java, and this is another big difference between Java and C arrays, in Java every single array has a public final int field in an array that's called length. And so every array will have this length field, and you can access it and figure out how many items there are in the array. In C, things are just a little bit more raw. That is, if you have an array, for example, an int array of size 10, as is declared here, you just have 10 ints. That's it. No indication of how many things there are in the array. So you have to keep track. You, the programmer, you have to keep track of how many things there are in each array. And if you call f, this function f, and pass it this array x, that function f will have no idea how big this array is. All it knows is that it has an array. It could be one element, it could be 0 elements, it could be 2 million elements. It doesn't know unless you give it some indication. So that's why we pass in a value 10 for this int n, and then it's up to the programmer of this function to make sure that this n is interpreted as the size of this array. So there's nothing in the language that sort of tells you, okay, the size of this array is given by the next parameter. This is just a programming convention that you, the programmer, whoever who writes the G function or the F function, you have to keep track of all of this stuff. Okay, so there's no function that will take as parameter A and tell you how big the array is. There are ways to find that information, but it's not simple. Definitely not portable in every situation, for every compiler and every hardware or every CPU. So it's best to, when you pass in the array, pass in the size, how many elements are valid. And if you make a mistake, like if you actually pass in an array of 10 elements and pass in the value 11, then you're probably okay. But if you pass in the value 5, this loop might end up doing the wrong thing. Actually, 5 is probably okay. But if you pass in a larger value, if you pass in 11, chances are this loop will go out of bounds. And so you'll get either some erroneous result, or the program might crash, or might go into an infinite loop like we saw in the previous example. Okay, so once again, C does allow arrays as arguments to functions. You can pass arrays into functions, but the thing is, the function may not know how big the array is, so you have to pass in the size as well.